Alright, so I'm going to walk through some unbalanced force problems with you guys just to give you a sense of where we're headed, right? Remember, the unbalanced force model, right, is pretty well connected to our constant acceleration model. So as we move into this, we're going to be applying things that we applied to the constant acceleration model, right? That is the big four kinematic equations. But for now, let's just focus on unbalanced forces in terms of Newton's second law, F net equals mass times acceleration. So to start off pretty simple here in this first problem, my scenario here is there's a flat section of ground, there's a box that, let's say the box weighs, I don't know, we'll say it weighs 2 kilograms. And there's a dude here who's pushing the box and he's accelerating the box in this direction. Okay, so the box is accelerating. When you see that there's acceleration, you know it's unbalanced forces. So the question here, right, might be what is the acceleration of the box? And first thing we might do to consider this would be draw a free body diagram, right? So I've already kind of outlined one here. This would be the normal force, gravitational force. This is some kinetic friction, and this is, we'll call it force of the dude pushing him, or pushing the box rather. So when we look at this, right, I've drawn it kind of to scale. The box is accelerating in this direction here, right? So it would make sense that F net, right, also has to follow that direction. So there won't be any F net vertically in the y direction, so the force of gravity and the normal force are going to equal each other, especially since we're on flat ground, right? However, the friction force and the force the guy is applying cannot equal each other, or else we wouldn't have any acceleration. So our question here is dealing in the horizontal direction. What is this F net? What is the difference between these two forces? Let's say, to make it simple, I'm just going to give you the friction force. I'm going to say there's a friction force of 150 newtons acting on this box. Now, if I had given you I gave you the mass, right? So if I gave you the friction coefficient, you could solve for friction using a couple steps, right? You could solve for Fg, which equals Fn, and then use this equation, which was tricky for some people on your quiz, right, to solve for the friction force. I'm not going to make you do that here. I'm just going to give it to you. It's 150. And let's say that the dude is pushing with a force of 200 newtons, just so we get a feel of this. So we've got 200 newtons and 150 newtons, but they're in different directions, right? So if we add their vectors together, right, kind of a shorter one and then a longer one, right? This is our dude and this is FK. The difference between these two is going to be in this direction, right, just as we predicted, and its magnitude is going to be the difference between these two values, so 50 newtons, right? So F net equals 50 newtons, and I'm just going to say to the left. Okay, and now we can apply Newton's second law, F net equals ma, right? And we have the mass of the box, so we can figure out the acceleration, right? 50 newtons equals 2 kilograms times acceleration. So the acceleration of this box is going to be 25 meters per second squared. From that, right, when you solve for the acceleration, we could, if you had a little more information, solve for a bunch of different things using the big four. So that's where we're headed here. Moving on to a slightly more complicated example. Say you have a 10 kilogram box that is sitting at the top of a 30-degree slope. Okay, 10 kilograms. It's stationary, so it starts with an initial velocity of 0, and then it starts accelerating down the ramp, right, sliding down the ramp. And the question is here, what is the acceleration of the box? And I'm going to give you the friction force again. Let's say that the kinetic friction force is 10 newtons. Right, first step would be to draw a free body diagram, which I've already kind of done for you. Then FG. And now, right, we're going to want to kind of mirror what we did before. We know the box is accelerating this direction. Right, there's our acceleration. So F net must also be in that direction. So we're going to have some net force this way. So that means that in the y direction, if we split into components here, right, FGY is going to equal Fn, because we're balanced this way. The box isn't kind of floating off of the ramp. However, in this case, right, FGY is going to have some component of F net, right? We know that FGX, that FGX must be greater than the friction force, right? Because it kind of overpowers the friction force and ends up giving an F net in this direction. And we know that if we take the difference between these two, we're going to get the magnitude of F net, right? I'm putting absolute values around here because it can get tricky with if you denote, right, that this is positive over here and this is negative, right? Remember, these don't denote values, they denote direction. So if you're looking for the magnitude, it's best to just kind of leave the signs out, subtract the smaller value from the larger value, and then denote direction using your vector. So now we go back to our system for solving for values from balanced force, right? We know that this angle is 30 degrees. So we could solve for FGX using sine 30 times FG, right? And we know FG because FG equals mg, always true. So that's going to be 98 newtons. Sine of 30 equals 1/2, so FGX is going to equal 49 newtons, right? We were given the friction force in this case. However, right, if I were to give you, again, mu k, you could, for that surface, you could solve for the vertical component, relate that to the normal force, and then use this equation again to solve for friction. So there are ways that you can do that, and that sort of incorporates what we've been looking at balanced forces. So back to where we were. FGX equals 49. That means that we have a component of this vector here that's 49 newtons. So then if we look at this equation here, 49 newtons minus Fk was given as 10 newtons. The F net is going to be 39 newtons sort of down and to the left, right, in this direction, down the ramp. So if we want to know the acceleration, we just plug in 39 equals mass times acceleration. The mass of the box is 10 kilograms. So divide both sides by 10, you get 3.9 meters per second squared equals acceleration. So that box is going to start accelerating down the ramp at a acceleration of 9.8 meters per second squared. A quick note here, this equation, the F net equals ma, is where it's really important to remember that 1 Newton equals a kilogram meter over second squared, right? Because you're relating these two, and if you look, right, you're essentially saying if we break down these units, right, force is going to be in newtons, mass will be in kilograms, and acceleration should be in meters per second squared. So these units are equivalent, right? Which is why you can relate newtons to kilograms to meters per second squared. But make sure that, if you're asked to solve for an acceleration, your answer should not be in newtons or kilograms, right? It should be in the correct unit for that object, right? That value. Okay, feel free to watch this video a couple times. We'll be going over this in class too. But essentially, right, once you get the hang of figuring out what direction F net is in and how to solve for its magnitude, you can do all sorts of crazy stuff around objects and how they're moving and what direction they're moving.